Hey all, this is Dr. Kamal. I wanted to make a quick video on Anova. The title here is experimental design because these slides delve into the experimental design, but we will not get that far in this video, maybe in another video. So today we'll talk only about the Anova, analysis of variance. We'll talk about one-way Anova. If we get a chance, we might talk about the two-way Anova at this time. We will not talk about the randomized block or the experimental design in this video, but maybe in a subsequent video. The Anova terminology is a response or dependent variable, and this can be only one, cannot be multiple. Independent variable, and this can be one or more, so it can be one independent variable or several independent variables or two independent variables. There is something called treatments. There is something called factors and levels. This is a quick example on treatments and response variable. In this particular example, the gasoline mileage case, does gasoline mileage vary with gasoline type? If you go to the gas station and you have regular, medium, or premium gas, if you put one of each and try, would you make more miles for each? This is the question. So we will call these type A, B, and C. And we will go ahead and collect observations between three. And these observations, as you see in these three columns, they might have differences. That's what we're trying to explore. We call these in-between variability. Within each column, within these observations, the 5 observation here, for example, is what we call within variability. So we will compare, basically in the Anova, compare the in-between variation to the within variation, and we'll see which one is larger. Usually the within variation is due to randomness. It's normal variation, cannot change it, but in-between variation can depend as another source. There might be another source of variation. So visually, these are the 3 types. They look visually different in this particular case, but that does not mean you can rely on that visual look to make calculations. You need to make the calculations to get the numbers for verification. You can use the visual for a quick glance on if there's are differences or not. The response variable here is the miles per gallon. The treatments are the ABC, or the different types of gas. And this can apply if you are in a factory or a mill and you have 3 shifts. So the shift 1, 2, and 3, or morning, afternoon, and night shifts will be the 3 different treatments. If you work in a bank and you have 3 different locations, so these different locations will be the treatments, and so on and so forth. The geographic region, different countries, these are all called treatments. If you have groups of people, you can call them treatments, and so on. Group 1, Group 2, Group 3, and so on and so forth. The concept here is we are going to assume that the mean miles per gallon in all gas types are the same. Hence the null hypothesis, all means are equal. The alternative is at least 2 of them are different, and if 2 are different, that means they're not all the same. Basically, we are comparing the between treatment variability to the within treatment variability, and see if this is larger than this one. Then there is variation. This is just a visual. In this case, A, between treatment variability is not large. They're very close together, A, B, C. But in this one, they are very large together. This is, bear with me for a second, this is what Excel gives out to you, but you need to know what Excel is giving out to you, so you have that expertise. Basically, Excel calculates total variation between variation, within variation. The total is basically the sum of these two. To calculate the total variation, Excel uses something called total sums of squares, or sum of squares, equal to the treatment sum of squares, the error sum of squares. The sum of squares is basically the difference between each observation and the mean, and that difference is squared, and then these squared differences are summed, and that creates the sum of squares. If you apply it to the total, then it becomes of the total. If you apply it only to the treatment or the error, and so on. The error is the within variation. We call it error because it's a random error. It's just normal. Is not changed by anything. The treatment might have an impact, and so SSTO equals SST plus SSE. These are the mathematical formulas of how these statistically are calculated. And if you notice here, this is the summation from 1 to p, the summation from 1 to n, xij minus x bar squared. This is the sum to squares. This is the difference, squared difference. And if you go back to these, here you will find A1, A2, B1, C1, and so on. These are the ij's, and this is 1, 2, 3, 4, 5. So it will be the j up to 5, and p will be 1, 2, 3. So p can go to 3 from 1 to 3. Just to give you a quick understanding, from 1 to 3 for the treatments, 1 to 5 for the observations, and this is I1, I2, I3, and so on and so forth. And you can build the rest of the equations the same way, or you can understand the rest of it. So the sum of squares total is equal to the sum of squared differences between each observation and the total mean. And the sum squares treatment is the sums of the number of observations per each treatment multiplied by the squared difference between treatment mean and total mean. The sum squares of error is the sum of the squared difference between each observation and treatment mean. If you put this in Excel, and this is just a manual calculation first, here are the treatments A, B, C, here are the observations. Treatment mean is the mean of each column. Sum of squares is here, xi minus x total squared. Sum squared total is 1704. For example, the x total is 35, and so on and so forth. This is just manual calculations if you want to follow these to understand how this works. Excel calculates something called the F statistic with the Anova. The F statistic is basically the sum squares of the treatment divided by degrees of freedom, p minus 1, divided totally by the sum squares of error, but divided by another degree of freedom, which is n minus p. This is how Excel works. You don't have to memorize these, but you need to understand how Excel goes about to bring you the numbers that you use to make decisions. We reject the hypothesis that all means are equal for all the treatments if the F calculated, which is here the statistic, is larger than the F critical, which call it F alpha, depending on the significance level. Sometimes you want to use the p-value. P-value is the probability of rejection. If p-value is less than alpha, then you still the significance level, then you still reject the null hypothesis. So this is like the door, and if your F statistic is here somewhere, if not still larger than the door, then you're still within the room, and so on. If you pass the F critical, you get to be rejected. So here you are one of the group, everything is okay, but if you exceed that, then you get rejected. So this area, all the means are the same. If F critical exceeds the F statistic, exceed the F critical, get into this zone, it's rejected because it's no longer part of the group. There are differences, and this is how you understand that. The p-value, if you want to learn, p-value starts from here and grows this way. This is what's the opposite. So if alpha is larger than p, if p-value is here and alpha is 5 is larger than it, everything is still in the rejection zone as well. Here is again what the Excel value the table would look like. Excel will give you this, sums of squares, F value critical will give you between groups, here, between groups, within groups, and will give you the total, and they will give you, for example, here, whatever is in red is an explanation of what Excel is calculating for you. In this case, F critical is a statistic, is larger, much larger than F critical. And therefore, what do? We exceeded the door. We came out of the door. So this is rejected because the F statistic is larger than F critical and so on. Also, p-value is 0.005 or 0.01. And if your significance value is 0.05, then it is less than it is less than the significance level. It's the same way rejected. In Excel, you will go to data analysis tool pack, data analysis, and you will select Anova single factor, and then you will highlight the treatment. Notice the boundaries of the selection. Notice that you have alpha here is 0.05. You select the labels and you will hit enter, and Excel will give you this, will give you a little summary, and this is the Anova table that we were just looking at. This is the treatment effect p-value, or you can compare the two. The p-value is usually quicker visually to make comparison. If you know your alpha is 0.05, clearly different, but you still can compare the F statistic to the F critical. We'll stop here, and this is the visual again. You can use that mileage per gallon. You will see the difference between the two. These are the observations of each column, and this is the mean of each column, and you can see there are visual differences and so on. We'll stop here in this video. Afterwards is another group, one way Anova in Excel. We'll see if we have enough time to go through. These are the 3 columns with different values. We want to do them in Excel, and let me get back here. I'm gonna let you look into this. If you want to try this in your Excel and see what you're going to come up with, fine. You can ask questions on the comments in the channel here, and I'm happy to respond to that as well. But we'll stop here, and we'll talk about the random blocks in a different video. Thanks so much.